Okay, so I have returned. Hopefully, you gave those last two questions a bit of a thought as to what the oxidation numbers would be. So let's take a look here. We sort of saw from the previous video that if there's a charge on the ion, then the oxidation number is just that charge. So that's pretty straightforward. Um, and then if we saw a compound like sodium sulfide, we know sodium is +1. You got two of them, so that's +2. And the oxidation number on the sulfur would have to add, or have to be a number that adds to 2, gives you an overall charge of 0. Um, so if we use that same technique for oxygen here, we actually find out some interesting things about oxygen. And so what we might say is, well, the hydrogens in H2O2, they each have a +1. So that would be 2, just kind of like above. That's from the two hydrogens, two H's. And then the oxygen would have its own oxidation number, but we have two of them. So we have 2 times whatever X is, whatever the oxidation number is, and that gives us a net charge of 0. So this number at the very end here is what we're going to call the net charge. And that's the charge on the overall species itself. So H2O2, there's no charge written up here, so I'm assuming it's a charge of 0. So it's charge of 0. And of course, if I solve that now, I get 2x equals -2, and then divide by 2, and I get x equals -1, which I think is probably maybe unexpected at this level of chemistry, that the oxidation number on the oxygen here, so on the oxygen, so the sulfur was -2 up there. So on this oxygen, it's actually a -1 oxidation number. What do you think about the diatomic molecule of oxygen gas? Well, if we use the same technique here, we could say that, well, we've got two oxygens. So we've got two oxygens, and they would have an oxidation number. And the net charge on that is 0, which means we divide by 2, and we get 0 divided by 2, which is 0, which means this oxygen, in that form anyway, would have an oxidation number of 0. Now you might say, well, no, my teacher told me back in grade 10 that oxygen's -2. It's always -2. Well, if that was true, and you had two oxygens joined together, you had O2, then you would have 2 times -2, which means you should actually have a net charge of -4. And I've never seen O2 written like that. Like, I've never seen it written that way. So this is a bit, it kind of spans ionic compounds, but also with covalent compounds. And we can see that oxygen actually has multiple oxidation numbers, or combining capacities too, they sometimes call them. So if we look at, in the case of, like, let's say, sodium oxide, so from the last test, the last unit, it's an oxide, a metal oxide, so that would be extremely basic. That this oxygen here, it would have an oxidation number of -2. And the reason for that would be that you have two sodiums, each one has a +1 charge, so 2, plus the oxidation number for oxygen, giving you a net charge of 0. So that would give us an oxidation number of -2. So just in that one example, or sorry, with this one situation, you can see that oxygen actually has multiple oxidation numbers. So which one do we go with then? Well, thankfully, there's only two sort of obscure cases, which is if it's in the form of a diatomic. So if it's in the form of a diatomic, then oxygen will always be 0 for its oxidation number. And if it's ever in a peroxide, which is what this is, in the form of peroxide, like hydrogen peroxide, then the oxidation number is -1. So other than that, it's always going to be -2, or I should say not always. Always is such a strong word in science. It's like 99% of the time going to be -2. There's always a chance. There's a weird chemical out there that I don't know about, and I don't want to get myself caught up in some kind of specific loop here. But oxygen in a diatomic state, so O2 is always 0, and in a peroxide, it's always -1, and generally with everything else, it's going to be -2. So let's look at some more, maybe more challenging cases here, and let me just find a good example. So let's take a look at where are we here? Bromine, or sorry, BrO3 minus. Okay, and the question is, what is the oxidation number on the Br here? Okay, so what is the oxidation number on that Br? Okay, so I'm going to introduce you to a formula that I think you should try to use. And this is, you take the positive items and you add them to the negative items. The negatives will have a negative charge, so you'll actually be subtracting when you do that. And that's always going to give you the net charge on the compound. So this is sort of the formula I would get you to kind of work with. It's a pretty easy formula. You're taking positive things, adding negative things, and then getting a net charge overall. And so I'm going to take this example here, Br. Now, what's strange here is that Br is in the halogen column, and so I would normally think bromine should be a negative charge. We're going to show you where it's not actually, and that's because oxygen is a -2 in this case. The oxygen in this compound is not in the diatomic form of O2 gas, and this is not a peroxide. So what we're going to say is we have X for bromine, plus, now I've got 3 oxygens, okay? Each one has a -2 charge, and my overall compound actually has a -1 charge. So that's the overall exponent you'll see up here, okay? So if I work that out, I get X minus 6 equals -1. So then I add 6 to both sides, and I get plus 5. So the oxidation number here is plus 5. Now that might seem kind of strange in the beginning, for many reasons. One is it's large, and the other one is it's positive, which is really strange. But if bromine had a negative charge and you combined it with 3 oxygens, each having a -2 charge, then you would think the overall charge would be -7, but it's actually -1 here. Okay, so I'm going to just give you a few more examples, and once again, this does take a bit of practice to kind of get good at. Let's take a look at ClO2 and minus. See if you can answer that one. And let's try I2, iodine. And let's try, oh, that's a good one. Cr2, so chromium, dichromate, O7, and a -2 on there. Okay, so try those ones, but pause the video, see what you think, and then I'll just continue on here. Okay, so I'm going to look at the oxidation number on the chlorides. I probably should have told you what you're looking for. Oxidation number on the chloride, oxidation number on the iodine, and oxidation number on the chromium here. Okay, so I've got X for the chloride. And once again, my brain initially, when I was probably in grade 11 or 12, I would have thought it should be a negative number here. But when I actually look at the rules here, I'm going to say, well, I'm going to go X, and then I have to add 2 times -2, because there's 2 oxygens with a -2 charge, and overall -1. So X minus 4 equals -1. So I add 4 to both sides, so X is equal to +3. So this is a +3, the chloride has a +3 oxidation number, okay? Now the iodine, well, I know that I have 2 of them, so I'll say 2 times X. And there's no charge here, so it's 0. So I divide by 2, and I get X equals 0. So this iodine has a 0 oxidation number here. And don't forget, I think for a lot of people, that might seem strange, because you probably remember iodide, the ion, iodide, has a -1 charge. But this is not iodide. This is a covalently bonded molecule, which is iodine, the iodine molecule, diatomic. Okay. So this polyatomic ion has a -2 charge, so that's the net charge, but I've got 2 chromiums, let's say 2X plus, and then let's stick with I like this color, 2X, there we go. And I'm going to add, and then I've got oxygen, which has, I've got 7 oxygens, each with a -2 charge, because once again, this is not diatomic oxygen gas, and it's not a peroxide, and an overall charge of -2. So when I work that out, I get 2X minus 14 equals -2. I add 14 to both sides. So I get -2 plus 14, which is 12. And then I divide by 2, which gives me 6. So the chromium, each chromium here has a +6 oxidation number. And you can check this pretty quickly. If you said 2 times 6 is 12, 7 times -2 is -14, that should equal -2. And so you can kind of just double check your math if you're not too sure about that. Okay, so what about a chemical where maybe there's like some brackets in the form? I'm just trying to think of a good example of this. Let's think of aluminum. Yeah, that might work. Yeah, let's try that. Let's try aluminum. And then something like OH minus on the outside, but a 4 down here. Okay. So this compound's kind of tricky because you've got this OH group that has a 4 written as a subscript. So you have 4 of those, but really just one aluminum. So what I would do is I would just use the same setup here. I would say, well, I have X for my aluminum. So X is the aluminum. And then I've got, now there's a couple different ways you could do this. You could treat OH as an entire group and think about its overall oxidation number, or you could treat the oxygens and the hydrogens as separate entities if you wanted to. So I'll do it both ways, see what happens. So I could say +4 times -2, because I've got 4 oxygen atoms. And now I'm going to add 4 times +1 for the hydrogen, and overall equals -1. So this is for the oxygen, and that's for the hydrogen. So I have X minus 8 plus 4 equals -1. So X minus 4 equals -1. So X is equal to -1 plus 4, which is 3. So I would say this is the 3 plus aluminum ion here. But let's just double check that the other way, okay? So let's say that you do X plus, now if you have OH, the oxygen has a -2 and the H has a +1, right? So really that thing in the brackets is a net -1, okay? And you've got 4 of those things. So 4 times -1 equals a net charge of -1. And of course, that's X minus 4 equals -1, which is the statement we had here. So obviously the X still must be 3, okay? So there are a few different ways to tackle these kind of problems, but hopefully that kind of makes sense for you, okay? So let's take a look at a reaction and figure out, is it actually a reduction oxidation reaction? So is it one of these fancy reactions? And so in order for it to be a redox reaction, something has to get reduced and something has to get oxidized. And if that doesn't happen, then it's not a redox reaction. There's lots of different reactions out there. We've seen from the last chapter neutralization reactions, and we've seen combustion reactions. And so redox reactions, as they're referred to, redox, have to have 2 things going for it. You have to have something being reduced, and you have to have something else being oxidized. So a redox reaction is one in which one species gets reduced and one gets oxidized, which means one species has to be a reducing agent and the other species has to be an oxidizing agent. So this question we've already done before, so this is sort of obvious that this is a reduction oxidation reaction. But what you would look for is, first of all, is there a charge change? Is there a change to charge during the reaction? In this case here, we have definitely removed electrons. And so that means the charge has gone up, so that's got to be the oxidation reaction. And the silver ions, they've gone down in charge, so that's the reduction reaction, which of course makes the silver ions the oxidizing agent and makes the copper metal the reducing agent in this case. So this would definitely be a redox reaction, classified as a redox reaction, okay? But let's say you had one that wasn't so clear, like what was actually going on here. And so I'm going to make sure I write this down right here. So just give me a second here. So 2 IO3 plus 5 bromides plus 7H pluses goes to form I2 plus 5HOBr plus water. Cold brews. I saw that before somewhere. Plus waters, okay? And someone says to you, well, is this a redox reaction? I mean, it looks ugly, so maybe, but is it actually one? I'm just gonna have a sip of my coffee, sorry. Delicious. Okay, so in order for it to be a redox reaction, something has to get reduced and something has to get oxidized. So what I would look at is, first of all, is look for atoms that are seem to clearly change their oxidation numbers. So generally a good way to look for that is what we call single species groups. So that means you just have just that atom. Like something like Hobra, that's a bit complicated, but look on the far left side here, you got this Br minus, okay? And it has a -1 charge here, okay? So I might want to work with that, or I could even work with the iodine, because that's just I right there. So let's work out their oxidation numbers. I'll use red for their oxidation numbers. So here the oxidation number is -1, okay? And for the iodine, it's got no overall charge, so its oxidation number must be 0. Okay, so the bromines, it seems like they are turning into this Hobra stuff here. So what I would really want to know is the Br in that compound, is it still -1, or has it actually changed to a different oxidation number? And if it's changed to a different oxidation number, then it probably has been reduced, or it has been oxidized. So let's figure that out. So I'm just going to draw a little arrow like this, just trying to find that. So I have +1 for the hydrogen. I have -2 for the oxygen, and I have X for the bromine. And the net charge is 0, okay? So that would be X -1 equals 0, which means X is equal to +1. So it actually is a +1 now. So it went from being -1 to +1. So that's definitely funny. So that would mean something happened to the oxidation state of it, which means it's gone from negative to positive. So did it gain electrons or lose electrons? Well, it would have had to lose electrons to do that. In fact, it would have had to lose 2 electrons to do that. So this is definitely Leo goes Ger, right? So losing electrons is oxidation. Now, of course, if there's oxidation going on, that means the bromide ions, they would be the reducing agent, which means they would be causing something else to get reduced. So what could be getting reduced? So let's take a look at the I's here. You've got I2, which is a 0 charge. And now I'm going to go look at the I in this compound here, okay? And I'm hoping that this is going to show reduction, because otherwise it'd be strange for 2 oxidation reactions to take place, because then like where are these electrons, where do they go, right? Okay, so let's say X is the I, and then I have to go -6. So I'm just going to shortcut it here, because I know the oxygens are -2. I've got 3 of them, so -6. And I'm getting a net charge of -1 for that species. So I add 6 to both sides, and I get a +5 then. So this actually is +5, okay? So you went from a +5 state, to a minus, let's scribble that out, sorry guys, to a 0 state. So that is definitely reduction. I reduced it by actually 5 electrons. Okay, so this is definitely a redox reaction, and sometimes you have to do that. You actually have to look at the oxidation numbers and figure out, did something actually happen to it here? Okay, so let's take a look at one more example of this kind right here. Okay, so let's take a look at H2SO4 reacting with barium chloride, and you're told this forms barium sulfate and HCl. Okay, so what I'm going to look at here is let's look at the sulfates. You can actually look at sulfur as an individual chemical, or you can actually look at sulfate as an actual ion here. And what I mean by that is that sulfate has a -2 charge. And so the sulfur here would have a certain oxidation number, which we could work out pretty quickly, but let's pretend we didn't know what it was, okay? So this here is sulfate, and this over here is also sulfate. And of course, sulfate's sulfate. So the sulfur here would have to have the same oxidation number as the sulfur there. Now you could work it out if you wanted to. You could say, well, I know that's x minus 8 because of the oxygens equals -2. So I add 8 and I get 6. So that has an oxidation number of 6. And of course, you could work it out as the sulfate itself and say, well, this compound has a -2, and we know hydrogen has a +1, and I've got 2 of them, and overall there's 0 charge. So that kind of, I could look at it as sulfate as a separate polyatomic ion, or I could break it apart into this, into its atoms if I really wanted to. But anyway, I know barium, that's an alkaline earth metal, so that's going to be +2. And I know sulfate's -2, and that's 0. So it seems like nothing has happened to the oxidation number on the sulfur. And we know that oxygen is going to be -2 here because it's not a peroxide or a diatomic state. And hydrogen is always +1. So it looks like the sulfates, nothing's occurred here. So what about the barium? Well, barium, once again, that is an alkaline earth metal. So that's going to be +2. And that's got to be +2, the second column of your periodic table. So maybe the chlorides, we've seen a few examples where the chlorides do change oxidation number. In fact, we've seen examples where chloride has a positive charge. But here you would have 2 plus 2x equaling 0. Not sure why I just drew that weird bracket. And that means that you would have 2x equals -2. So x equals -1. So each of these chlorides is a -1 oxidation number. And of course, we've got HCl on the far side, which is a +1. And then we're going to go plus, no, yeah, minus, right? Plus x, right? We don't know what it is. Plus x equals 0. And of course, here, bring the 1 over, x equals -1. So really, if you notice the chemicals, there is no change in oxidation number here. So this would not be a redox reaction. So this is not redox. So if you have a redox reaction, something has to get reduced and something else has to get oxidized. You can't really have one without the other. Because if you reduce something, you have to give it electrons, and those electrons have to come from somewhere. And if you're giving your electrons away, well, then you have to give them to something. So once you oxidize something, something else gets reduced. There are just shortcuts to figure out whether something's going to reduce or oxidize. It's going to show you quickly something like this. Let's see if that's CL minus. Make sure that chromium, and you turn that into CrO4 2 minus. Okay, so here's two different reactions, and the question is, which one of these is reduction, which one's oxidation, or are they both reduction, or are they both oxidation? So you could use oxidation numbers. That's going to work pretty quickly for you. This clearly is +3, and this chromium would be x minus 8 equals -2. So this would be x equals 6. Okay, so clearly that looks like oxidation to me. That's oxidation reaction. Charge has gone up. No reduction going on here. Okay, so oxidation, that's Leo, so losing electrons. And let's see what the next one is. Well, here you have x minus 8 equals -1, so x equals 7. So this is +7. And then over here you have x minus 6 equals -1, so you get x equals 5. And so that's clearly going to be that's clearly a reduction. Okay, so that's one way to do it, doing those. But there is a shortcut you can do here, and it does involve around not so much math, but just thinking what's happened to the compound here. And so I'm going to get you to look at the second example here. Here we go from a chemical that has no oxygens, and then you've stuck some oxygens onto it. So clearly we've added oxygens to it. And that actually is originally sort of where the wording comes from here. So that has undergone oxidation. Okay. And if you look at the other example, you have 3 oxygens on that side, and you have 4 oxygens on this side. So if you were to go this way, you would be adding oxygens, which means this way would be oxidation. Which means the other way would be reduction. So in terms of oxidation, you can just sometimes look at how many oxygens there are. And one way to think about that is if you had AO, let's say 2, so some chemical called AO2, and you turned it to AO4, you've added more oxygens, so it would have to be oxidation. But think about the math on this. If A had a value of X, you'd be minusing 4 and getting 0, right? And of course, in the other one, you'd still have A minusing 8 now and getting 0. So you can see that the X value would have to get bigger as you go across, and that's characteristic of oxidation reactions. So I just wanted to show you that because sometimes you can just look at the equation, not have to work out oxidation numbers. Although I would be careful if you have something where maybe you have like AO2 and you're going to AO4, but now it's like A2O4. So be careful about subscripts if you're using this little trick here. Maybe using oxidation numbers in that case would be a better way to go. Okay. Okay, so let's talk about what no one wants to talk about in this chapter is the data table. So if you can turn to the data table on this, we're going to talk briefly about that. Okay, so I'm going to see if I can share that. So I'm going to pause my video here while I do that. Okay, guys, so I think I got this working here. So if we look at your last page of your data table, it's called the standard reduction potentials of half cells. And this is a killer data table to look at, or killer sheet on the data table to look at. It is quite full of information. And I'm not going to do too much on this today, but I kind of wanted to orient yourself a little bit to get a sense of how to read the data table. So a few things. I'm going to do another video on this. So if you feel a little bit lost, that's okay, because it does take a bit of time to get through. What I want you to notice is the left-hand column here, actually left-hand arrow. You notice that it's kind of similar to the acid-base data table, where it pointed up on the left side. That usually meant like a stronger acid, or maybe a stronger weak acid. And on the right side of the acid-base, I'll just sort of show that. There you go. So there's your relative acid-base strengths. Goes up on the left side, goes down on the right side. So this last data table has something similar to that. But notice it's not talking about obviously acids and bases. It's talking about the strength of the oxidizing agents and the strength of the reducing agents. So remember, this is where it does get tricky, is that oxidizing agents cause something else to get oxidized. So what actually happens to oxidizing agents then? So if they cause something to get oxidized, they themselves must wind up getting reduced. So they're the things that actually take electrons away. So they take the electrons. And the reducing agents, they're the things that cause something else to get reduced. So if they cause something else to get reduced, they themselves must be oxidized. So that does take a bit of time for your brain to kind of click to that. But if you get confused, if you're like, you're like, I still just can't get this after a couple of days of working on it, look at the data table's headers. Like, look at the headers on the data table. And so if you look at the very top here, the left-hand side are the oxidizing agents, and the right-hand side are the reducing agents. And I'm going to ignore this voltage thing right now, okay? So let's look at fluorine gas, okay? So if fluorine gas is given 2 electrons, well, if you give something electrons, what are you doing to it? Well, gaining electrons is reduction. Remember, Leo the lion goes, grrr. So gaining electrons is reduction. And if you get reduced, you must be an oxidizing agent because you're causing something else to get oxidized. So therefore, yourself, you get reduced. And notice that everything under the oxidizing agents, they all have different names or different symbols and stuff, but notice they're all plus some number of electrons. So for the first one, you get fluorine plus 2 electrons, then S2O8 2- plus 2 electrons, then so on, and maybe down there's gold, 3 plus 3 electrons. And so all those chemicals under the oxidizing agent column, they're all gaining electrons. So they're all being reduced. And then on the right-hand side, you have the reducing agents, which is what they turn into. Now, if you're not sure about this, let's just pick fluorine, for example, here. Fluorine would have an oxidation number of 0 because it's diatomic. And then you're giving it 2 electrons, and that's going to produce 2 fluorine, F minus, and 2 of them would be a -2 charge. This is why you need 2 electrons. So you went from F having a 0 to F having a -1. So that is reduction. You've reduced the charge on that. Now, the other ones might be harder to see, like this S2O8. You would have to do that thing we did earlier about breaking it into the parts, like, and then making like SX. You have like 2x, 2x minus 8 equals -2. So that would be 2x equals 2x equals 6, divided by 2 is 3. So you probably would find here each sulfur has 3, a charge of 3, but then you have SO4 2 on the far side, and that would be, what would that be? X minus 8 equals -2. So X would equal, where are we here? 6 here. So I'm going to work this out with my pencil here. I'm getting tired here. So I had 2x minus, minus 16, sorry, because there's 8 oxygens, equals -2. So I botched the first one. I already saw my mistake here. So 2x here would equal -2 plus 16 is 14. So the oxidation number would be 7 on the S2O8 sulfurs. And then on the SO4 side, you would have X minus 8 equals -2, which is X equals 6. Yeah, so definitely a reduction going on there. And so you could do that for all these compounds, but why bother? They've already told you that, right? They've told you the oxidizing agents get reduced. So just a few other things to look at. And once again, I'm going to do more on this data table because it is horrendously killer. Is there's a lot of chemicals that appear more than once, and that's what makes it quite confusing. But sort of like amphiprotic compounds in the other unit that we did. So for example, I'm going to just sort of, I can't draw on this one, unfortunately. I think I can annotate. I'll annotate here. There we go. Annotate. So here, you'll notice that you have copper 2 plus, right? So there it is under the oxidizing agent, so it can be reduced into copper metal. But here you got copper 2 plus, so it can also be reduced into copper 1 plus. So that's kind of confusing, kind of different here. And whoops, I'm still on annotation mode. Can I move? Oh, I can't. I have to turn that off. Let's do. Oh, actually, it'll work here. But look at this here. Here's let's do a different color here. Here's tin 2 plus. So there's tin 2 plus being reduced into tin metal. But here's tin 2 plus being oxidized into tin 4 plus. So that's, I know, I find that kind of confusing, lots of different places. And you got lots of examples of that kind. So this table is definitely, I think, harder to read than the acid-base table. It does take more practice. And I would really encourage you, I know you guys are getting tired. I've talked to a few students and you guys are getting spent of all this stuff. But I would try to devote a little more time to this unit. And once it clicks for you, though, I mean, I found a lot of students, they said, oh, no, I totally get how the table works. And they actually find the chapter quite easy, like once they get their head around how the table works. So I would really encourage you, before you go to bed tonight, just bring this table out and just start reading it. I mean, I guarantee you it'll make you fall asleep. Okay, it's that stimulating. Okay, anyway, so just keep plugging away at it. We got another roughly 4 weeks to go. You guys have been doing awesome. Try to keep in with things and hand in your assignments. And then our next tests, as you may know, has been moved to next Tuesday. And I did ask you guys to get back to me if you had a conflict between your Block A and Block C classes running on the same day. So if on next Tuesday you have a Block A class and Block C class running on the same day, I'd like you to email me about that. Okay, and if I don't hear back from you, I'm going to assume the answer to that is no. Okay. So anyways, I hope you guys are doing well, and we will talk to you in a wee bit.